Up until this point, you may have been asking yourself, what is the importance of balancing equations? So in this section here, we're going to discuss what quantitative information we can gain from balanced equations. And specifically, we'll talk about later on this chapter what stoichiometric calculations we can perform, such as calculating how much product we could yield for a reaction. So what type of information can we gain from a balanced chemical reaction? So here's in this first row here, an example of a chemical equation where we have 2 moles, or in our first scenario here, we could say we have 2 molecules of H2. So we have 2 H2 in gaseous state. And then we could again represent that as 2 molecules, or in reality, it's probably more likely that 2 moles of H2 would react. But notice that that coefficient 2, depending on how you're looking at this reaction, can apply to both molecules and moles equally. So then we see that we have 1 mole of oxygen, or 1 molecule of O2 in this first scenario, and then 1 mole down here, which these 2 moles of H2 and 1 mole of O2 produce 2 moles of liquid water. So that's where this coefficient 2 comes in. And we can think of that again as 2 molecules of water, or more likely, in reality, probably 2 moles of water. So down at the bottom here, we can look in this last row, and the mass of 2 moles of H2 is approximately 4 grams. The mass of 1 mole of O2, so 16 plus 16 for oxygen, is 32 grams. And our product, 2 moles of water at about 18 grams per mole, gives us 36 grams of H2O. And we can see that on the reactant side and then on the product side, mass is conserved. So this ratio, again, of the in the balanced equation tells us the moles of our reactants and products. And if we are given a starting material and we're told what molar ratio we have in an equation, we can predict how many moles of product we make, for example. So let's take a look here at this flow chart, and say we start up here with this reaction where we see C6H12O6 and 6 moles of O2 produce 6 moles of CO2 and 6 moles of H2O. So we can't directly calculate if we start with 1 gram of glucose here, how many grams of water can we produce? So we have to use this kind of roundabout calculation here and say, if I'm given 1 gram, so 1.00 gram of glucose, if I divide by the molar mass of glucose is about 180. That will get me to how many moles I have. So that's this intermediate value right there. And then if I was to multiply for every 1 mole of glucose, I can produce 6 moles of H2O. That brings me to this point right here, where this would be the mass of H2O that I can produce, or rather how many moles of H2O I can produce using that molar ratio of 6 to 1. And then in this last step, I could use the molar mass of water, and I would multiply here that for every 1 mole of H2O, that's about 18 grams. And then when I multiply that last step, that brings me to this value here. So we always have to get to a intermediate of moles. So generally you would be given a value in grams or milligrams, convert that to moles using the molar mass in grams per mole. And then at that point, use the balanced equation, like we did here, to say that for every 1 mole of glucose, we could produce 6 moles of H2O. And that molar ratio is this middle conversion factor. And then lastly, we multiply by the molar mass of what we're trying to find if we want to find our quantity in grams. So we can use this information to help us solve sample exercise 16 here. And we're told that we have decomposition of potassium chlorate, and we're given the balanced chemical reaction here. So if we need to prepare a small quantity of O2, we're told that sometimes this balanced reaction is used, or this reaction in general is used. So we have 2 moles of potassium chlorate, solid, and say we heat that or we decompose it in some other fashion, that can produce 2 moles of potassium chloride, solid, and 3 moles of O2 gas. So we want to know how many grams of O2 can be prepared from 4.50 grams of potassium chlorate. So we always start with what we're given. So we're given 4.50 grams of KCl3. And first step is to get this to moles. So I would calculate the molar mass. So I have 39.098 for potassium. Chlorine, Cl, is 35.45. And then I add to that 48 for 3 oxygens. So for every 1 mole of KClO3, the mass is about 122.45 grams. So I'll divide by that, and now I can assume that I'm in moles of potassium chlorate, and I can use the molar ratio now of 2 to 3 to figure out how many moles of O2 I could produce. So it's 2 moles of KClO3 on the bottom, and then we multiply by 3 moles of O2 on top. And I don't want to stop there because I was asked to find my value in grams of O2. So I know that for every 1 mole, there's 2 oxygens, so that's 32 grams. So I put that in the numerator. And if I plug in all these values, I would multiply 4.5 by 3 by 32, divide by 122.45, and then again by 2. I would find that I could make about 1.76 grams of O2 using this reaction here and that quantity of potassium chlorate.